Hello everyone. Welcome to the SWAYAM NPTEL course on mathematical geophysics. We will be starting the module number 7, that is thermofluidic processes in geophysics. This is the first lecture of this module, Laplace's and Poisson's equation. In this lecture, we are going to cover the mathematical aspects such as Laplace's equation and Poisson's equation related to the thermofluidic processes in geophysics. The thermofluidic processes which are dependent upon these equations will be considered in further lectures. In this lecture, the four components are as follows: the Laplace's equation and its solution, then the extension to Poisson's equation, and various applications in geophysics. So let us begin. First, we consider the Laplace's equation. We have seen the Laplacian operator in previous lectures. This is the Laplacian operator. We have the Laplacian equation based on this operator acting upon a field and equals to 0 on the right hand side. The Laplacian of any scalar function going to 0 is the Laplace equation. This is a second order partial differential equation. We have seen the occurrence of Laplace equation in potential theory such as gravity and electromagnetism. It describes the conditions for the potential, which is gravity potential or magnetic potential, such that there are no net source or sink of the field. Thus, Laplace equation can be understood in physical sense as representing the steady state or equilibrium condition where there are no net source or sink of the field. In other words, the Laplace's equation governs systems where a conserved quantity such as velocity, potential or temperature balances out over a region, which means that the Laplacian equals 0. Its solutions are known as harmonic functions. Now, we will look into the various forms of the Laplacian equation in different coordinate systems. We had looked at glimpse of such equations in very few previous lectures, in very first few lectures. In Cartesian coordinates, the Laplacian equation is represented as del square by del x square of f plus del square by del y square of f plus del square by del z square of f equals 0. Now, these are constant coefficient partial differential equation. In spherical coordinate systems, which are more prevalent and appropriate for geophysical systems, the Laplace equation is given as 1 by r square del by del r of r square del by del r del f and 1 by r square sine theta del by del theta of sine theta del by del theta f and 1 by r square sine square theta del square f by del phi square equals 0. Now, these three terms represent the individual Laplacian components of the Laplace equation in radial, azimuthal and meridional angular directions. Note the presence of variable coefficients in this partial differential equation. This variable coefficient also occur in cylindrical coordinate system representation of the Laplace equation. Thus, in spherical and cylindrical coordinate systems, the Laplace equation is a variable coefficient PD. Now we will attempt the solution of Laplace equation. We have chosen the spherical coordinate system because the solution of Laplace equation in spherical coordinate systems is very important for geophysical applications. The solution of Laplace equation in spherical coordinate system leads to the Legendre polynomial system and the spherical harmonics. Thus, it is very important to understand the solution of Laplace's equation in spherical coordinate system for geophysical purposes. We have the Laplace equation in spherical coordinates, unto which we introduce the variable separation form of f. F being a function of r theta phi can be separated out as the product of capital R, capital T and capital P functions. These are individual functions of r only and theta only and phi only coordinates. Now, substituting this variable separation form of the function f into the Laplace's equation as given by equation 1, we obtain equation 3 given by this, where the appropriate substitutions have been made. Note the coefficients of these three terms as they appear in the Laplace equation components. The first term, which is the radial component, has t and p as the functions in the coefficient, which means r is absent. Similarly, the component theta has the function capital T absent in its coefficient. Function p is absent in the coefficient for the phi term. Thus, we can introduce the corresponding functions by dividing the entire equation 3 by r, t, p. This gives equation number 4. We have also multiplied r square sine square theta such that there are no r term in the denominator. This factor r in the denominator is removed in equation 4 by multiplying r square sine square theta. The factor such as this sine theta is also removed from equation 4 denominator by multiplying r square sine square theta. Now, the purpose of multiplying this and removing r and sine theta from the denominator is to avoid any singularity. As singularity can occur in equation 3 for r equal to 0, theta equal to 0 coordinates, which is the center of the sphere. To remove this singularity, we have the regular equation 4 instead of the singular equation 3. We can simplify equation 4 to equation 5 in a manner such that the left hand side contains r and theta, and on the right hand side we have only function of phi. Now, since the left hand side is function of r theta and right hand side is function of phi only, this means that both these left hand sides and right hand sides are constant. That constant is assumed to be m square. Now we move on to obtain the phi component solution for the Laplace equation. We consider the phi part. Del square p by del phi square plus m square p goes to 0. This is an ordinary differential equation whose solution we have discussed in previous lectures. Assuming p as exponential form given by capital A e to the power p phi and substituting into equation 7, we can obtain the phi solution as p equals a cos m phi plus b sin m phi. These are sinusoidal functions. Equation 8 represents the phi solution of the Laplace equation. Now we move on to find the r and theta solutions of the Laplace equation. First, let us consider m equals 0. If m goes to 0, we have this equation. We can separate out the two terms as equation number 9. The left hand side depends only on r, while the right hand side depends only on theta. Now, this variable separation form can be treated such that each individual left hand side or right hand side becomes equal to some constant. Now this constant is L into L plus 1. Where L is a constant quantity. We will soon understand the purpose of choosing such a form for the right hand side constant factor. Now let us look into the R solution. The R solution can be proceeded as follows. 1 by r d by dr of r square dr by dr equals L into L plus 1. The capital R is a function of r only. This gives r square d square r by dr square plus 2r dr by dr minus L into L plus 1 capital R equals 0. Now this is an ordinary differential equation which we can solve for assuming the form of the solution as C r to the power alpha. Here we have a polynomial expansion such that the functions of R are polynomials. Substituting it into equation number 12, we get the algebraic equation number 13. Alpha minus L multiplied by alpha plus L plus 1 equals 0. This gives alpha equals to L or alpha equals to minus L plus 1. One can try to obtain the interim steps between 12 and 13 for practice. Just by substituting C r to the power alpha, it can be easily done. Having the two solutions L and minus L plus 1 gives two solutions for R. Note that the combination of these two solutions gives the general solution for R. C R to the power L plus D R to the power minus L plus 1. We can understand these two components as the rising component and the falling component because R to the power L increases in its magnitude with increase in R, while C R to the power minus L minus 1 falls or diminishes in its magnitude as R increases. The rising part is the first and the falling part is the second component. These are the two ways in which the radial variation of the Laplacian equation can be understood. Now we come to the theta solution. Similar to the R solution, we proceed with the constant minus L into L plus 1. It gives the following equation number 14. Now consider x equals cos theta. We are substituting x in place of cos theta because we want to represent the solution in form of polynomials. Thus, we are having the aim to convert the trigonometric form to polynomial form. Now, substituting x as cos theta and sin theta appropriately, given by root over of 1 minus x square, we have equation number 14 given by 1 by root over of 1 minus x square with the bracketed quantity having minus root over of 1 minus x square and minus 1 minus x square dt by dx plus L into L plus 1 capital T equals 0. This can be simplified into equation number 17 and finally equation number 18, which reads 1 minus x square del square t by del x square minus 2x del t by del x plus L into L plus 1 t equals 0. Equation number 18 is the celebrated Legendre equation, and the solution for t are the celebrated Legendre polynomial series. The Legendre polynomial series are given by P with subscript L. Thus PL cos theta or PLx is the Legendre polynomial. Now we can see that the Laplace's equation can lead to Legendre polynomial with the subscript L denoting the degree of the polynomial. This can be related to the spherical harmonics where Legendre polynomial is used in theta, and in phi we have the sinusoidal components. Thus, this functions sinusoidal in phi and Legendre in theta makes the spherical harmonics. Thus, the spherical harmonics are nothing but the combination of theta and phi solutions of the Laplace equation in spherical coordinate system. Thus, we come to the general solution, that is the product of R, T and P. Thus, the function f can be written as the sum of all the linear combinations of the R part the phi solution and the theta solution. This is the most general solution of the Laplace equation in spherical coordinate system. We look into the next Poisson's equation, which is the inhomogeneous form of the Laplace equation. We have Laplacian of f equals to s, where s is a non-zero quantity. Now, the need for Poisson's equation arises when we have fields or systems where sources are present. To account for the source, the introduction of the term on the right hand side s is necessary. Thus, the term s on the right hand side of the Poisson's equation accounts for the presence of source or sink terms in systems which are otherwise composed of conservative fields. Thus, to clearly differentiate Laplace's equation and Poisson's equation, we can say that Laplace's equation there are no source or sinks, whereas Poisson's equation there is a non-zero source or sink term. It represents the generation or absorption of various field quantities. Now, we look into the application of Laplace's and Poisson's equation in geophysics. These equations are widely used to understand various phenomena in Earth's subsurface, atmosphere, and magnetic field and gravitational fields. In magnetic and gravitational fields, which are conservative fields, there may be the presence of anomalous sources of gravity and magnetic field in the form of high density material or magnetic field generators. The presence of such sources would require the use of Poisson's equation, while the understanding of these fields without any sources will require the use of Laplace's equation. Specifically, gravitational field modeling requires the Poisson's equation to be used for calculating the potential in regions where the mass density acts as a source. And Laplace's equation is used to model gravitational field in free space, where the source is absent. Such regions are above the Earth's surface, while below the Earth's surface, Poisson's equation is more appropriate for gravitational field modeling. Next, we have the magnetic field modeling. Similar to the gravitational field modeling, Poisson's equation is appropriate for understanding subsurface magnetization. Below the surface of the Earth, high electrical conductivity bodies may exist which can act as source or sinks of magnetic field or electric current when geophysical methods based on induced polarization or resistivity methods are used. Above the Earth's surface, the magnetic field is devoid of any magnetic sources, and in such regions, Laplace's equation can be used. Note that in regions such as ionospheric regions where magnetic or electric currents can exist, the Poisson's equation may be more appropriate. Thus, we can see that the combination and interplay of various systems in geophysical applications would require the appropriate choice of Laplace's equation or Poisson's equation to model the phenomena. Thus, we come to the conclusion for this lecture. The Laplace's equation describes steady state or equilibrium conditions without sources and sinks. It governs phenomena which involve conservative fields such as gravitational potential, electric potential, and temperature in source-free regions. The solution of Laplace's equation are very important for geophysical modeling. These solutions are called harmonic functions, and the solutions for the theta component result in Legendre polynomials, while the solution in phi component result in Fourier components or sinusoidal functions. Overall, these two combinedly give the spherical harmonic functions, which are very much appropriate to model surface related functions on a sphere. The Laplace equation is more appropriate for modeling fields in free space, voids, or equilibrium systems. On the other hand, Poisson's equation, which is the inhomogeneous form of Laplace equation, can accommodate the existence of source or sink terms. It extends the applicability of the Laplace equation, but it comes at a more challenging cost as the solution of Poisson's equation is more intricate than the Laplace equation. This is because the solution of Poisson equation depends upon the nature of the source term. Thus, the solution of Poisson's equation varies from case to case basis. Overall, it can be said that the Poisson's equation describes how physical quantities are influenced by localized disturbances or source and distributed sources. One can have a look into the following reference for more details on Laplace's equation and Poisson's equation. Various applications related to geophysical phenomena are also discussed in these references. Thank you.